Well, hello there guys, Mr. G here, and in this video we're going to be making lesson 6. Now lesson 6 is going to be a law. It's going to be the law of conservation of momentum. Now we did previously Newton's law. I'm not talking about in terms of momentum, but Newton's law of motion. Now we can solve a big number of questions or problem using Newton's law of motion, but not all the problems can be solved. For instance, if the time of interaction is very small, then we cannot solve those problems. In some cases are very difficult to use. So that is why we are going to learn about the law of conservation of momentum. It's a very important law, a principle. Some people call them principles, some people call them a law. So watch the video. Thank you for watching. Subscribe. I'll see you next lesson. This time we're going to be doing conservation of momentum. This is lesson 6. Now, before we start with the conservation of momentum, we must talk about certain definitions, certain things important before we understand about conservation of momentum. And the first thing we're going to mention and very quick go through is what is a system, because systems are important in this topic. So we're going to first of all write down and define and speak and explain what is a system. So what is a system? A system is a small part of the universe that we are considering when solving a particular problem. It's a small part of the universe that we consider. We are deciding which one is the system. Okay, so the system is whatever we decide to be, but it's not the whole universe. So the system could be a small part inside the universe. Now, everything that is outside the system that we consider, then it's going to be the environment. For example, let's say a ball is dropped. Okay, now what is acting on that ball? Is acting air. There is the gravitational force through the earth. So if we consider that the system is going to be the ball and the earth which is pulling the ball towards its center, then the system is the ball and the earth. Everything outside that is the environment. For example, the air is the environment, is not part of the system. It is there, it does exist, but it's not part of our system. We're going to see that one in an example now. For example, we have a wall and we have a ball which is moving towards the wall. As you can see there, it's moving in that direction. Okay, it's moving in that direction. Now the ball bounces on the wall and moves in the opposite direction. So for us here, the system is going to be the ball and the wall. The order of the word doesn't matter. You don't even have to write. You have to identify. So everything else that is not ball and wall is outside the system. For example, the earth is not part of our system. For example, the earth here is not part of our system. It is there, it does exist, but it's not part of our system. Somebody must have thrown that ball. A person somewhere must have thrown that ball, but that person is not part of the system. Our system is only going to be the ball and the wall. So I hope this part to understand system is already understood. It's very, very, very easy. Now, systems can either be open or closed. Systems. We have system that could be open or can be closed. Now, let's quickly mention and explain this one real fast. Now, what is an open system? Is a system where the environment interact with the system. That is a open system. For example, in this case, if there is a lot of air, the air will affect badly on the motion of the ball. Therefore, that system is going to be open. Now, when a system is going to be closed, when there is not interaction between the system and the environment, or the interaction is minimum. We can say also that it's closed or isolated. However, it is not exactly the same. So let's write here isolated, but it's not exactly the same. An isolated system is where energy cannot be transferred throughout the system, from system to outside or so on. Okay, but we're going to use either terms, either closed or isolated. Now, when the system is closed, that means that no matter from outside is interacting or affecting our system. So if the system is closed or isolated, means that we can completely ignore the environment. The environment is there, but it's not affecting that system of us. That's why we can ignore. Let's say we ignore. The environment exists. Please note, when we say closed, it is like a idea. The system is there, the environment exists, and somehow the environment may affect the system, but not that much. If it's not affecting the system so much, we said the system is closed or isolated, and that means that we can ignore the environment. For example, here in the case of the balls, we ignore the air, even though obvious you cannot take off all the air, but the air is so little that we can ignore, and the air is pulling the balls down, but because the system is very small here, we are going to ignore the force of gravity because it's also small. Okay, so that is important to know. Now, there is something also very important, which is forces. Now, according to the type of system, which is either open or closed, forces can be divided in two main groups as well, which are internal and external. Let's write here external forces, and let's write here internal forces. Internal forces. Now, the relation is the following. If the system is open, there will be external forces acting on the system. So there is a relation between that. For example, if the air here is very big, it's a lot of wind, let's say, then the system is open, and the forces of the wind, of the forces that the wind exerts on the ball, are going to be called external forces. All right, so everything that is coming from outside the system is going to be called external forces. For example, the force of gravity here, which is not part of our system. Remember, our system was the ball and the wall only. The air is not part of the system. So the force of gravity in this example is an external force. So that is very important to have in mind. We need it. Okay, so we can say that external forces arise as a result of the interaction between objects of the system with objects outside the system. So it's those forces between objects from outside the system with any object from the system. For example, in this example here, only in this example, every system is different, guys. So in this example, the force of gravity would be an external force, because the system we mentioned, I'm going to highlight it again here, the system we mentioned was the wall and the ball. So everything outside that is an external. The force of gravity will be an external force in this system. You cannot learn gravitational force is going to be always an external force, because it depends on the system. Now, what are the internal forces? Now, the internal forces are the forces within the system. For example, in this situation of the wall and the ball, the force that the wall exerts on the ball will be an internal force. Is the force between the part of the system. That is what we call internal forces. So we can say that internal forces are forces which act between the objects of the system. So we're going back again to this example just for last time. The system is ball and wall, so the gravitational force is going to be an external force. The force of the resistant force of the wind, if there is any, will be an external force. The force that this person here applied on the ball at certain time is going to be an external force. What will internal force be? The force that the wall here exerts on the ball when the ball bounces on the wall, and the force that the ball exerts on the wall. Those are the internal forces in this system. Remember, all the systems are different. It depends what system you select, okay? And it is a very important thing. Now, when the system is closed, and I'm going to write here in a closed or isolated system, what we have, we know that the net external, I'm going to write external forces, is going to be equal to 0, because if the system is isolated, there won't be any external forces. So I want you to know that I'm talking about the external forces. Okay, so in an isolated system, the external forces of the net external forces is 0. And this is what we just learned. Okay, now if we remember that impulse is equal to external forces multiplied by time, or net forces multiplied by time. That means that the impulse of the net force, the time here, will also be 0. Okay? That means that the impulse that is being produced by the external forces is also going to be 0. If the net force is 0, the impulse is 0. Okay? This is coming from here. We are working with the isolated system. Remember, we're working with the isolated system. Right? Now, remember the impulse momentum theorem. We know that impulse is equal to change in momentum. Impulse is equal to the change in momentum. So if the external impulse, or the impulse done by the external forces, is 0, so thus the change in momentum is also equal to 0. Here we are. We can say that the change in momentum, remember we work in change in momentum, is going to be equal to 0. There we go. Okay. Now, what is change in momentum? Change in momentum is final momentum minus initial momentum, and all that is equal to 0. All right. Now, if we rearrange this one, we'll have that the whole momentum initial will be equal to total momentum final, and this is, my lovely children, what we call the conservation of momentum. Now this here is the conservation of momentum, but note something important which I'm going to add now. We're talking about total momentum. Total momentum initial and total momentum final. So this is total momentum and this is total momentum. So what can we say? If the initial momentum is equal to the final momentum, we can conclude that in the isolated system, total momentum initial is equal to total momentum final. And this is what we call the law of conservation of momentum. So this law states that in a closed or isolated system, the total momentum is constant. It's very, very useful. We're going to use it a lot, but remember something very important here. The system must be closed. We cannot apply this law if the system is not closed. So this is something to have in mind. And now this is happening during any interaction, like we cannot solve using Newton's law. For example, when you have an explosion, or when you have a interaction between objects in which the time of interaction is very, very small. So as usual, let's try to look at one example. Okay, so let's look at this example. This example said a rifle of mass 4 kilograms fires a bullet of mass 3 times 10 to the minus 2 kilograms at an initial speed of 700 meters per second. Calculate the velocity with which the rifle strikes the gunman's shoulder as it recoils. Let's first of all have a little drawing of the situation here. Okay? And here is the situation. Now, what we have here, we have a man with a rifle, and inside the rifle is the bullet. Now, what is going to be the system for us? The system is going to be the rifle and the bullet. The rifle and the bullet is what is important for our system. So the man is not part of the system. The man is there, it is holding the rifle, but we are not going to be doing anything with the man. It's outside the system. Okay, so the system is going to be the rifle and the bullet. And we have two important situations here. Or let's rather say we have two momentums here. We have a before the rifle shoot the bullet, and we have an after. Okay, and this is very important. We have to divide this question in two parts. We have a before and we have an after. Now, for example, the mass of the bullet and the rifle did not change in either case, before or after. Mass of the rifle, I'm going to write an R for rifle, is going to be equal to 4 kilograms. The mass of the bullet, and I'm going to write a B for bullet, is going to be equal to 3 times 10 to the minus 2 kilograms. Now, the velocities are a little bit tricky here. Initially, we are at before. So, if you can see, neither the bullet or the rifles are moving. So, the initial velocity here for the rifle is equal to 0, and the initial velocity of the bullet is going to be equal to 0. So this is important. This is data. I'm going to write it on that side. Now here, after what happened? That person shoot the bullet. The rifle shoot the bullet, and the bullet leave the rifle with a velocity which is going to be equal to 700 meters per second forward in that direction. Let's say forward. They don't speak if it's right, left, east, west, or whatever. It's to the right. So that is the initial velocity of the rifle. But the initial velocity is, in actual fact, is a after velocity, because it's after it's been shot. Okay. And now this rifle, as a result, will move backward. It will move. Let's do it at the bottom here. This rifle will move in that direction, and that is the question that they ask you to calculate that velocity. So we cannot use Newton's law here. It's a little bit difficult. It's too difficult to use Newton's law. So we're rather going to use the law of conservation of momentum, okay, that we just learned. Now, you don't have to write everything that is here. You don't have to write all that. It's not necessarily. You can already start from change in momentum. We say the change in momentum is equal to 0. We having that this system is closed. We are only working with the rifle and the bullet. So it's a closed system. Closed system. You don't have to write this. It's just telling you the system is closed. So from here, you don't have to go, but you can write the total initial momentum. Remember, this is total, is equal to the total final momentum. This is total initial equal to total final. Now, what is total initial? That is the initial momentum of the rifle plus the initial, all this is initial, let's write the initial. That is the initial momentum of the rifle plus the initial momentum of the bullet. And this is going to be equal to the total final momentum. What is that? That is the final momentum of the rifle plus the final momentum of the bullet. And this, my lovely children, is the law of conservation of momentum, right? So now remember that momentum is equal to the product of mass and velocity of an object. We are going to substitute that formula in each of the different momentums here. Okay, so we have, let's say it's another page, we're going to have the mass of the rifle multiplied by the initial velocity of the rifle plus the mass of the bullet multiplied by the initial velocity of the bullet is going to be equal to mass of the rifle multiplied by the final velocity of the rifle plus the mass of the bullet multiplied by the final velocity of the bullet. And in this question, as we did previously, it is important to select direction. So we are going to select forward as positive. And obvious, in this case, the bullet is moving forward and it's the only data we have. But remember, this is very important, okay? So we're going to carry on here. Now you are ready to substitute. Now, if you go here, you can see that at the beginning, the objects are together. the rifle and the bullets are together as a unit. So if you want, you can say here using a common factor, which is the initial velocity of both of them, and multiply the mass of the rifle plus the mass of the bullet. But that is up to you. If you don't want to do it, don't do it. You can substitute straight there, and maybe even better just to not get penalized. Okay, so and this one is mass of the rifle, final velocity of the rifle, plus mass of the bullet, final velocity of the bullet. So we are now going to substitute. The velocity initial of both of them is 0, and the mass I am going to substitute, even though the product will be 0, but I am going to substitute that masses there. So the mass of the rifle is going to be 4 kilograms, plus mass of the bullet is going to be 3 times 10 to the minus 2, and equal to mass of the rifle is 4, initial velocity or final velocity of the rifle, that is what they're asking you to calculate. It's a vector. It should keep all vectors notation. Remember I said it's not a must here in South Africa, but let's keep it to keep the physics correct. Plus in this side is the mass of the bullet, which is 3 times 10 to the minus 2 multiplied by the final velocity of the bullet, which is the velocity with which leave the rifle, and is 700 meters per second. Let's just close the bracket here, and this is just simple math now, simple calculation, which I don't doubt that you can do it. So the final answer here, the final velocity of the rifle is going to be equal to minus 5,25 meters per second. Remember what I always tell you, the minus here means direction. So to be safe, guys, let's going to write the final velocity of the rifle is equal to 5,25 meters per second in the opposite direction. Opposite direction, and this is all related to the example. Okay, this is the final answer for this example. I hope you understand. This is all about the topic. We can quickly look very quickly look at the lesson. First of all, we spoke about system. Remember, the system is a small part of the universe that we select. Everything else is the environment. Here we have a ball that bounces on the wall. The ball on the wall is the system, so everything else is going to be the environment. The system can be open or closed. The open system, there is interaction between the system and the environment, but the closed system or isolated, there is not interaction. Forces could be external or internal. We can actually say that an open system is the one that have external forces, and the isolated or closed system is the one that do not have external forces, and all the forces are called internal. Now, if the system is isolated, we can say that momentum does not change. This is the meaning of this one here. Momentum does not change, and that is the law of conservation of momentum. In a closed or isolated system, the total momentum is constant, and then we did one example. Next video is going to be doing some questions related to momentum and the law of conservation of momentum, and I'll see you next time. Thank you for watching. Thumb up, subscribe. Thank you, Mr. G here.